Hello everyone, welcome to the 9th lecture on deep learning. Today we're going to be looking at flow models and also a little bit at implicit representation networks. So far we've looked at approximating the max likelihood equations through variational inference, through adversarial games and so on, but today we're going to be looking at what happens if we can restrict a set of functions in our deep neural network to get some very desirable characteristics. Specifically we'll be after the desirable characteristics which allow us to get tractable or exact likelihood estimation, where we can make sure that our data is always a valid probability density function and that we can actually therefore have a really nice exact generative model. So we're going to limit our functions to allow us to do this. And implicit representation networks are something else that we're going to just look at briefly towards the end, which have some very nice properties in terms of being able to support different types of data, specifically for continuous data. Okay. So today in the overview, flow models are, like I said, one of the more advanced aspects of deep learning. They're heavily based on the characteristics of the Jacobian. So we'll start with just a kind of brief recap of generative models and the Jacobian, and then we'll define what the determinant of the Jacobian is. And this determinant of the Jacobian is really essential to understanding how flow models work. And this is going to lead us nicely into what's called the change of variables theorem, and this allows us to renormalize the transformations in a deep neural network to ensure that all of the intermediate distributions all integrate to one. So we don't really need to approximate that integral in the denominator that we saw when we were covering energy-based models. We can actually do this exactly. So we'll then be defining normalizing flows and using the change of variables theorem, and we'll look into sort of how we design the layers in these networks, the flow layers whose determinants can be computed efficiently. So we'll be looking at some of the state-of-the-art papers, and we'll actually read together a recent one in detail. And lastly, we're going to cover these implicit representation networks, which, while these aren't necessarily generative models, they can actually be made into generative models. They do have some very interesting characteristics, especially for scientific computing. Okay, so just as a recap, if we remember the definition of what a generative model was, and we're basically trying to learn the joint distribution over some observable data, so call it X, and some target variables, say Y. And we want to be able to sample the model, or we want to be able to estimate the density of the model. So given some easy to sample distribution, we want to be able to basically feed this into our model and generate new samples, or just sample from some known distribution in the model. And with density estimation, we want to be able to take some data and estimate the likelihood of that data. And we looked at adversarial models and energy-based models. We looked at how energy-based models sort of push the fake values up and push the real values down, so that we can just start by taking some data sampled off the data manifold, and we can do gradient descent on it to move it down into the valley regions of the data manifold, such that as we do lots of gradient descent steps, our data starts to look more and more realistic. And then we looked at how GANs are basically doing the same thing, but instead of doing lots and lots of gradient descent steps, you just have some generator function which immediately tries to generate data into those valley regions of the manifold. So discriminators in GANs were also some kind of basically density model, but they don't actually give you a tractable likelihood. They just sort of try to make the data 1 everywhere where it's fake is 0 everywhere it's real, or vice versa, depending on how it's defined. Okay, so we've sort of started to cover the generative models of this form, but now we're going to be looking at flow-based generative models, which are a different type of generative model. And flow-based generative models are basically constructed by a sequence of invertible transforms. So unlike previous types of generative model we've introduced, a flow model explicitly learns the data distribution, or P of X, and therefore the loss function is simply the negative log likelihood, or if you like, maximizing the likelihood of the data. So if you remember way back when we looked at the sort of foundations of generative models, we looked at how we had some normal distribution over some data parameterized by the mean and the standard deviation, and we basically updated the parameters of mu and sigma to maximize the likelihood over the data, such that the data was most probable when according to the distribution. So we sort of shifted it the mu parameter, and then we shifted the standard deviation parameter to maximize the likelihood. So we can, if our functions are invertible, basically we can actually directly sample from the model. So to understand the maths of this, we're going to really need to examine more closely what's called the determinant of the Jacobian of our deep neural network. So we'll explain this in the next slide. But basically you can have one neural network, which this is the same neural network, or it's got the same parameters in it effectively, and this is just the inverse of this function. So long as you know the function and its inverse, you can take some data p of z, and you can slowly transform this distribution by these flow layers or these invertible transformations into hopefully something that looks like your actual observable data. And similarly, if you take the inverse of this function of this observable data, you should get exact points in your prior distribution, in say some normal distribution. And depending on how well you fit, it depends on the kind of quality of the observables you can sample from. If you take samples here, you sort of feed it backwards. Okay, so it's just one neural network which is simultaneously both allows you to do sampling and density estimation at the same time. Okay, so let's recap what the Jacobian matrix was, and recap our definition of it. And if you remember, we just said the Jacobian was a collection of all the first order partial derivatives of some vector valued function. So basically it allows us to differentiate vector valued functions of some domain Rn into some codomain Rm. So we can go from some domain to some codomain of different real spaces, different dimension. And basically we just calculate all of the partial derivatives for each of the functions individually with respect to each of the inputs. And this gives us our m by n matrix of partial derivatives. So if we think of this in the context of a deep neural network, this Jacobian basically tells us how much the inputs of a layer relate to its outputs. So for example, it tells us how much to tweak the inputs up or down, such as to minimize some output loss or objective. And in PyTorch, if you're probably quite familiar now, you can compute these with the torch.grad function, or you can just set like the requires grad to be true, and then you can use some leaf variable, you can do some intermediate computations in the forward pass, and then you can do torch.backwards, and that will backpropagate through to calculate the Jacobian for you. Okay, so that's the Jacobian, and hopefully you've kind of got some familiarity with this now. So we can move on to now the determinant of a matrix. So determinant is just some operation we can do on a matrix, but what we really care about is the determinant of the Jacobian matrix. And basically the determinant is a single value which tells us how much the area of the input space changes according to the linear transformation of the matrix M. Okay, so it's like this area. And actually, rather than me just try and explain it, there's a really, really great Free Blue One Brown's video here who does these very nice animated visual explanations, which would take me a lot. There's no point me reproducing it, I might as well just show you. So we're going to watch just, say, 3 minutes or so of this video together now, just because it's a really excellent visual explanation of what this is doing. It will help give us some intuition. So you can click this to watch the full video, but we're just going to highlight just up to sort of 4 minutes 45 seconds in. We'll watch this together now. Okay, so just...
This very special scaling factor, the factor by which a linear transformation changes any area, is called the determinant of that transformation. I'll show how to compute the determinant of a transformation using its matrix later on in this video, but understanding what it represents is, trust me, much more important than the computation. For example, the determinant of a transformation would be 3 if that transformation increases the area of a region by a factor of 3. The determinant of a transformation would be 1/2 if it squishes down all areas by a factor of 1/2. And the determinant of a 2D transformation is 0 if it squishes all of space onto a line, or even onto a single point, since then the area of any region would become 0. That last example will prove to be pretty important, It means that checking if the determinant of a given matrix is 0 will give a way of computing whether or not the transformation associated with that matrix squishes everything into a smaller dimension. You'll see in the next few videos why this is even a useful thing to think about, but for now I just want to lay down all of the visual intuition, which in and of itself is a beautiful thing to think about. Okay, I need to confess that what I've said so far is not quite right. The full concept of the determinant allows for negative values. But what would the idea of scaling an area by a negative amount even mean? This has to do with the idea of orientation. For example, notice how this transformation gives the sensation of flipping space over. If you were thinking of 2D space as a sheet of paper, a transformation like that one seems to turn over that sheet onto the other side. Any transformations that do this are said to invert the orientation of space. Another way to think about it is in terms of I hat and j hat. Notice that in their starting positions, j hat is to the left of I hat. If, after a transformation, j hat is now on the right of I hat, the orientation of space has been inverted. Whenever this happens, whenever the orientation of space is inverted, the determinant will be negative. The absolute value of the determinant, though, still tells you the factor by which areas have been scaled. For example, the matrix with columns 1, 1, and 2, -1 encodes a transformation that has determinant, I'll just tell you, -3.
Okay, so hopefully now you've got quite a clear visual intuition of what the determinant is doing, how it tells us how much the input space is being stretched by the output, being stretched by the function. So it sort of tells us how much that, you can imagine now how we can use it to see how much the probability density is getting distorted, or how much it's getting stretched by, so we can work out how to re-normalize it. So if the idea of what the determinant's doing to space isn't yet crystal clear with you, I strongly recommend you go back and watch this video here by Grant Sanderson, or Free Blue One Brown. Grant Sanderson, Free Blue One Brown video series is a really excellent way of learning some mathematical concepts. So do watch the full video if you would like to. Okay, so basically a non-zero determinant is very important for a linear transformation, as it means we can recover the data. As we saw in that video, if the determinant was 0, then basically it's getting squashed down into an irrecoverable state. So we really care about the determinant being non-zero. However, if the determinant of the Jacobian is 0, it means we can't. It does squish the data down a dimension in such a way that we can't invert it, we can't go back to it. So this is really what we want to avoid. And instead, we want to have invertible functions, or a chain of them, and we call this chain of invertible functions a flow. And they're just those which basically are functions which have non-zero determinants. Or if you like, we want the absolute value of the determinant to be greater than 0. That's just another way of saying it. It gives us a bit more flexibility to flip the space. So we want the absolute value of the determinant to be greater than 0. And actually, if we have a determinant of 1, this means that our function will be volume preserving. So if we know the determinant, we can use it to renormalize our probability distribution as it undergoes the transformation, such as to maximize the likelihood of the data. But unfortunately, calculating the determinant for large Jacobians is typically OM cubed. But if we constrain our neural network, we can actually reduce this to a linear computation of the determinants. So it's really about how can we efficiently implement this, or how can we efficiently compute it and retain these characteristics. That's really what the flow literature is about. Okay, so now look at this diagram at the bottom here first. As we start to draw some samples from a prior distribution, like a normal distribution, or anything which is really easy to sample from, it can be any prior distribution that you like, where we can evaluate the likelihood. So we're going to start by just drawing trace samples from distribution. But we know that the probability density function of this input distribution all integrates to 1, because we can just define it that way. We can define any distribution we like, which integrates to 1 that we can sample from. But if we just feed that into some just normal deep neural network, just design anything you like in PyTorch and feed it through, and what's going to really happen to it? What's going to happen to this function? Well, basically, we're going to end up with something which isn't a valid probability density function. You can imagine just applying any transformation you like to this function, You maybe stretch it in this way. There's no guarantee that the whole distribution integrates to 1 anymore. So it won't be a valid PDF. So we really need to renormalize it. We need to bring it right back down such that the whole thing integrates to 1 again. Okay. So for example, if our function caused the entire output volume to be stretched by a factor of 2, let's just say this is like stretched by a factor of 2, then we basically need to divide this resulting PDF by 2 to ensure it all integrates to 1. So how do we know how much to renormalize it by? Well, you've probably guessed it. We can use the determinant of the Jacobian of this function. Okay, so let's put this together now and build a generative model. So we have some prior distribution, pz of z, like a Gaussian here, which is just a function we can give it and sample, and it will tell us the probability of that sample. Then we have some observable, some x here, and this is just sampled from the data set according to some unknown data distribution. We can call this px of x, if you like. It's this unknown data distribution. Okay. And we also have some smooth bijection f. In other words, f is this function f is an invertible function where we can say that z equals, or z to prior here, equals the inverse f inverse of x. Okay, and this just basically means we can run our decoder neural network as if it were an encoder, and we know the inverse transform of its function, if we know the inverse transform of its function. So with this, now we can answer the question, like, what is the probability density function of the data? What is p of x, basically? And that's what we want to know. We want to know this density of the data, the likelihood of the data. And we can answer this using the change of variables theorem. And this is the theorem here. But basically, this theorem effectively describes how lengths, areas, and volumes, and basically generalized n-dimensional volumes, or the contents, are distorted by differentiable functions. So the change of variables theorem tells us that the probability of x is equal to the probability of your prior sampled via the inverse function at x, and then multiplied by the magnitude of the determinant of the Jacobian inverse. So the Jacobian of f inverse. Okay, so I'll probably read that again just because it's quite a lot to take in. So we basically say that the probability of x is equal to the probability of your prior, so this probability of your prior sampled via the inverse function sample by the inverse function at x, and then you multiply this through by this quantity here, which is renormalizing constant here, which is the magnitude or the absolute value of the determinant of the Jacobian of f inverse. So in other words, we evaluate the prior probability of an observation through the inverse of the model. So we run it like an encoder, but then we correct it by scaling it proportional to some value, which is calculated as the magnitude of the Jacobian of the inverse function. And so long as our functions are invertible and that this Jacobian determinant is easy to compute, then we can actually just use this method to exactly maximize the likelihood without any kind of approximations like with variational autoencoders or generative adversarial networks. So maybe I'll just give like an example for this to hopefully make it clear. Consider you have like some deep neural network function that has a scaling effect such that the output space is like scaled by a factor of 4. So you can just think of this as just some function which scales the output by 4. Then the determinant of the Jacobian of this function will therefore return 4. So now the change of variables formula multiplies through the magnitude of the inverse Jacobian, and this is actually all just the reciprocal, or if you like, 1 over the determinant of the original Jacobian. So this means we end up multiplying our stretched PDF by 1 over 4, which, as you can see, we'll just renormalize it such that it integrates back nicely to 1 again. Okay, so now we've defined that change of variables theorem, we can now start to talk about normalizing flows. So normalizing flows basically exploit the fact that we can easily compute the Jacobian determinant of composite mappings simply by multiplying the determinants of the individual transformations. So after we've initially sampled Z from some prior distribution, say from some Gaussian or something, basically it flows through a sequence of functions. So you take your Z and you flow it through a sequence of these functions where the density function is renormalized at each step. So every time you apply it through one of these functions, you basically renormalize it at each step. So you can imagine your input distribution Z here starting out as some nice normal distribution, and then you apply it to some transformation which sort of stretches it or modifies it, makes it maybe bimodal or multimodal, so it starts to look more and more complex. But every step that you make it more and more complex, you renormalize it, so it integrates back down to 1 again. And this is particularly useful in generative modeling, where we want to evaluate the likelihood of some observable data distribution P of x. So we want to basically try to transform the data, to transform the normal distribution such that it fits the data, and then basically if we can make it fit it pretty well, we can then actually just take any observation, and then we'll know the likelihood of it. So that's really basically what's going on. We start with some distribution and we try to move it through, distort it until it fits all of the observations, and we fit those observables as best as we possibly can. And once we've learnt that mapping, we know that at every point it's a valid probability density function at every step, integrating nicely to 1. So if we recap, previously we've seen how we can estimate the likelihood of the data distribution using those variational methods, and then we've also seen how we can approximate it using GANs and also with energy models. But now we're going to use a flow to derive an exact likelihood of the data, and this will allow us to both generate new samples, it will allow us to cluster samples together, build anomaly detectors, and so on. Okay, so let's walk through the equations for this. So x is our observed variable, so this could be like an image in our data set, but x is obtained through this flow. Okay, so it's obtained by passing z by some prior distribution P of z through a series of these bijective transformations of f. So basically x equals f of z with some parameters theta introduced into this chain of transformations. So now we want to derive our maximum likelihood objective using the change of variable formula. So first we basically take the log of both sides, and then we can replace the log determinant term with the sum of the log determinants of each of the intermediate Jacobians, and then we're basically done. So now we can basically directly train our model to maximize the likelihood of the data, and with this we can get this exact log likelihood evaluation, which is unlike the previous approximations we've seen so far. Okay. Alright, so now we have the sequence of high-dimensional bijective functions, but we need to somehow know how to compute the Jacobian determinants, and these can be really expensive. So instead what the literature tends to do is it tends to restrict the set of functions to only those with very easy to compute determinants. So it's like saying it's too difficult in the general case, so we're basically going to just choose functions in our deep neural network where we can basically have these really nice solutions to the determinant. And in particular, one really nice trick is what papers such as NICE, all in capital letters, NICE, and real MVP often like to do. And basically what they do is they ensure that the Jacobian matrix of the functions in their network or in their layers is triangular. And this is because the determinant of the Jacobian of a triangular matrix is simply the product of its diagonals. So if we look at this figure here, this is a lower triangular matrix, and you can simply determine the determinant of this matrix here by just taking the product of these diagonals. So you just do A11 times A22 times these values times ANN. So that's really super efficient to compute, and you don't need to do a lot of sort of switching around and reading. It's not OM cubed like in the full algorithm. So we don't really need to do any computation at all of the off-diagonals here. So it's in practice, in practice, if you remember the max likelihood equations, we only really care about the log determinant. So this is actually really convenient, as it means we can just take the log of the diagonals and then we can sum them. So we don't actually need to do a product which is the logarithm rule. So this is like a really nice. If we can ensure that our Jacobian is of this form, then it's just super efficient. And while the lower triangular matrix is like one such example of a really nice way, we can easily compute the log determinant. In practice, there are actually many ways we can construct functions which just have easy to compute in inverses and also log determinants. So basically, that's what the flow literature is doing. It's basically mathematicians and theoretical machine learning researchers just doing basically this. So they're finding functions which have quite nice capacity or quite nice ability to make the distribution more complex, more multimodal, and also those functions are those which have easy to compute inverses and easy to compute determinants. So here I've included a table which highlights several flow models, or if you like, these layers, and how their log determinant can be easily computed. And therefore, this gives like this tractable exact likelihood estimation. And if you open most of these papers here, you'll see how they also show you how to compute the inverse functions of the layers. So it really tells you everything you need to go about and do it. I just didn't have really space to show all of the inverses in this table here. So let's have a look at this. Let's open one of these papers here. So this one down here, citation 4, is GLOW generative flows with invertible 1x1 convolutions. That was in Advances in Neuralips. So that's a very reputable conference. So let's just Google that, GLOW generative flow models. Okay, models repetible 1x1. Okay, let's try and find this. Okay, I'm just going to download the PDF now. And basically we're just going to read this paper together so we can see how it fits in with the literature. So now you've got like this theory. I'll show you basically how you can quickly read a state-of-the-art paper to basically, this is what you should be doing in your own time in your own research and how you should be going about it. So the first thing you do with a paper is obviously you look at the title, you skim through the abstract and see if it sounds interesting to you. And then, oh, there's a nice figure here, so don't bother reading the introduction if you're in a hurry. Just see, do the results look good enough to warrant further inspection? And you can say, yeah, these faces look realistic. Things to particularly look out for are like, can the model capture high frequency variations, or is it just learning the expectation of the data? And here we see some nice face examples. So for every face image, we know exactly how probable it is, and we get an exact location in the latent variable. So let's now just scroll down. Might be nice to see if they've got some contributions highlighted. It's good to just basically jump into the maths and see if you're familiar with any of the equations. So the first two equations here just say that we want the loss to be the log likelihood of the data. And then at equation 3 here, it just says we have some prior distribution that we can sample from. And equation 4 then says we can obtain images x from our invertible function g of z. Okay, then equation 5 here just shows that x can be obtained by a flow, just like we've seen. You can get this x here by this flow, which is the sequence of transformations which get renormalized all of the time. And then equations 6 and 7 just show this change of variables theorem that we've just covered already. So actually most of the flow papers follow this very similar kind of format we covered earlier. Basically we can sum the log of the magnitude, or if you like, the absolute value of the determinant of the Jacobian. Okay, so let's keep going down. So equation 8 here, what's that saying? So this just shows basically we like simple transformations where the log determinant can be computed. So for example, we just like summing the log of the diagonals, which we saw in that matrix example, because this allows us to get these really nice efficient determinants. So basically, so again, all of the stuff we've just covered so far, it's just a very slight change in notation as per the author preferences. Okay, all right, so here we are. This is what we're looking for. So table 1 and figure 2 up here, basically This is the contribution of this paper here. So it's basically showing this very nice formulation here. So it's basically a new type of function, this 1-by-1 convolution, and they show its reverse here, or its inverse derivation, and they also show how to compute the log determinant in here, so how it can be calculated very easily. And then they show like some other flow layers of prior work. So we've got up here, we've got some other types just like this, where we've got the actual function, this ACNorm function, the inverse of it, and how the log determinant can be computed for that function. All right. And also, if we look at figure 2 here, it just shows how they like put these various functions together, how they can compose them together to create like a nice little mini block or mini architecture that they can chain together to create their more complicated architecture, which is able to, has the capacity, the representation ability to fit to that complex face data so well. Okay. Right, so let's just keep going down, see if there's any other equations or things we can look at. Okay, so here's another equation here. What's this saying? Basically just is giving more details of this function, and such as how it can be initialized with random rotations. So again, if you imagine a rotation like in that 3 blue 1 brown video, it didn't stretch the space, so you can actually initialize the functions with random rotations, which are all valid, still integrating to 1. So that's quite a nice little trick. And it seems like 9 to 11 are all just doing this. So it's just shifting basically some extra data on the initialization. Okay, so I think that's all the equations now. Now we go to the results. So basically just showing, yeah, it's a really good method. Look at the images, they look really, really nice. Doing some interpolations into latent space, and you can see that at every point in the intermediate values, the image, you can stop an interpolation at any point, and the intermediate points in that space still look like recognizable faces. So it's truly learned a nice representation of the data distribution from the observables. Okay, and then they're sampling the model trained on some bedrooms data set, and again the samples look quite good. Changing some of the parameters. So the results look quite convincing, and this is quite nice. They've also showed some of the code of their flow layer in particular, and so you can cross-reference this with that table. So let's just go and have a look at just that. So let's just look at the reverse computation here in the code. It says they start with the inverse of the weights matrix. So I'm sure if we go back to the table now and look at the inverse function, we'll see that's where it starts with. So I should get a faster scrolling mouse. So yeah, let's have it. So yeah, the start of their inverse function starts by just inverting the weights matrix, which is what they're doing in the code. Okay, so that's really useful that they provided that and helpful. It's often good to look to see if the authors have like a GitHub page as well to see if they've made any changes to their paper or results. But it gives you like another way of looking at the maths, just to see if sometimes authors will add a few little sort of extra tricks which they didn't have time or space to bring into the actual paper. So it's good to cross-reference with the code. But this looks quite sort of straightforward to what the table's showing. You've got the log determinant here, the forward function, and then the reverse function there, all implemented in a nice kind of little module. Okay, so that's really how what the flow literature is all about. Designing these chain functions here, which allow you to slowly transform your data into the observables, and it's very nice. It's kind of, if you're really like a purist, or you're really into doing things exactly and properly, you don't like any kind of approximations, then this is probably the literature for you. The main limitations of this are, of course, that you're adding these massive constraints now to your functions, especially in terms of not being able to compress the dimensionality down. So, but at the same time, you have this single model which simultaneously acts as you can sample from it, you can get the exact likelihood of the data with it, so it's very elegant from that perspective. Okay, and the literature all follows this nice kind of pattern. It's quite mathematical at times, but it's all it's all quite standard once you get to the grips with the foundations as we've seen today. All right, so now we're going to spend the remainder of the lecture looking at another type of model, which isn't actually a generative model, but it's still extremely relevant and quite new for scientific modeling. And also we're starting to see these models have applications in computer graphics too. And they're called implicit representation networks. So basically imagine that instead of training on an entire data set, we just train on a single image, or one piece of data, one sound file, or one video file. And what we want to do is we want to have a neural network represent that image, but in a continuous way. So try to sort of unlearn what you know about images and think of images as a function where you input to this function the x, y coordinates of a pixel. So like the pixel, you input, like I want the pixel value at coordinate 2 and 3. So that's the input of your function. And then the output of your function returns the color value of that pixel. So try to think of an image as something represented that way. So it's just a function where the input is the coordinates that you want to sample from, and the output is the value. And basically, this is a bit like how we did function approximators in reinforcement learning from the tabular methods. But basically what we do is we replace that NumPy array, that table of pixel data, with a neural network function, which we call phi. And then we try to approximate it using a neural network. So the input to the neural network has two neurons. So it has these X and Y neurons. And basically these allow you to specify the X and Y image coordinates that you wish to query at. So the inputs to the network are the two neurons for the X and for the Y coordinate that you wish to query at. So if you wanted to know the value of this pixel here, it's worth my saying that you would have to renormalize these. You typically, because the neural networks like the inputs to be 0 mean and variance 1, you normally make sure your coordinates are sort of to plus and minus 1, so they're renormalized by default. But let's say you wanted the value of this pixel here. The input to your neural network would be the coordinates of where that pixel was, so it would be -2 in the x-axis and -1 in the y-axis. If you wanted to query this pixel up here, that would be +1 and +1 would be the inputs to your neural network. And then the neural network is going to try and predict just the individual pixel value at that coordinate. And then you're just going to have some loss, which basically is how accurate you were or to estimating that pixel value, that color value there. So if you're trying to output an RGB image, you're going to have 3 output neurons. If you're trying to estimate a grayscale image, you're going to have 1 output neuron. If you're trying to estimate a 3D image or a volume like a medical CT scan, then you're going to have 3 input neurons for the X, Y, and Z coordinates. And if you're trying to estimate a video, then your inputs would be again 3 neurons. You would have the X coordinate, the Y coordinate, and then the value in time, which again you should renormalize. The value in time or the frame time for the pixel you're trying to estimate. And then the output again is just going to be a color value for that point in time at that coordinate in the video. Okay, and then basically what you would normally do is you would just use some standard loss like mean squared error on this. And then you backpropagate and you update the parameters of this neural network here, such as to like minimize that loss. And the whole process works quite well. You can do it for lots and lots of different types of data. You can do it for audio files as well. You would just have a single input coordinate for like an audio form. You just have the time along it. Then the output would be the amplitude of the waveform. And as well as images, videos, and sound, you can actually use these implicit representation networks to find a solution to wave fields and to solve challenging boundary value problems, such as the solution to the Eichel equation. And if you're not familiar with the Eichel equation, this basically lets you take as input an implicit surface, like for example like a binary object, which is negative on the inside and positive on the outside. and then it returns the signed distance for every coordinate in space. And you can also solve like the Poisson equation, the Helmholtz and the wave equations, and you can provide the implicit neural network the coordinates and or like higher order derivatives as input, and it will estimate the solution. And another really cool trick is that when the network is trained for this, you can actually sample in between the coordinates. So this is what starts to get really exciting. If you train this function here on a single image to represent that image, you can sample, like, because this is all continuous, you can sample between the actual pixel values that it was trained on, and this is going to learn a really smooth fitting to those values. So it'll actually infer between the pixels. So you could train on an MNIST at 28 cubed, and you can actually sample it at, well, sorry, you can train on an image from MNIST at 28 cubed, and then you can sample at any resolution, you know, at 8K resolution for a single MNIST digit. It would just look like a really large single MNIST digit. And also you can train on irregular data. So often with some data like protein geometry, you've got like this, proteins are represented as 3D points in space, but they're not regularly spaced. So for example, you might have a point over here, and then way over here you might have some other atoms, and some other atoms, and they sort of form some kind of spirally helix-like structure. And so what with this, you can just say, I know what the atom at this point, this coordinate in this real space should be. So you just provide the coordinates for where your atoms are, and then your output could be sort of the type of atom, whether it's carbon, oxygen, or it could be something else. It could be just the distance to the atoms, such that it should be like a signed distance function here. So you could say like the value, the distance should be 0 where the atoms are located, and it should be off 0 everywhere else. Okay, so also you can imagine applications like with training this with raw camera sensor data. You can query the function basically at infinite resolution. So if you imagine training videos this way, you can no longer be bound to sort of 4K or 8K resolution. You can actually have infinite resolution just based on you know how you query the model, and it can directly use as much of the camera's sensor data as possibly available to it. So it's got some very exciting applications down that sort of graphics application route as well. All right, so that's the basics of implicit representation networks. And now we're going to look at the most recent state-of-the-art paper from this field, which is called a SIREN, or a sinusoidal representation network. And this is really simply just, the function in here is just a bunch of fully connected layers or linear layers in PyTorch. So really nothing complex there. But instead of using ReLU activations, you remember that max of 0 and 1, which looks sort of straight and then straight up, it uses sine waves as the choice of the non-linearity sine functions. So you may be thinking like, so what? Why would that make a difference? Well, it turns out this actually makes a huge difference, as sine functions are periodic. You know, if you plot in Desmos sine function, you see it just goes on and on forever on the x-axis. So they repeat through all of the space. And if you recall, the inputs here to our network are the coordinates themselves. So this means that the network can actually learn to detect patterns over the entire domain, just like convolutions. So they're translation invariant. They become very, very parameter efficient, and they can actually fit to all the high frequency details of like textures. So imagine like you've got to be very careful how you initialize the functions. So you want quite a lot of waveforms over space. So you want like lots of high frequency variations over the coordinate space. So you want to sort of typically scale it by some value. But if you replace the nonlinear terms with sine functions, it means it can learn to fit to parts of the signal here, everywhere over the entire input domain. So it becomes translation invariant and very, very parameter efficient. But the main limitation of these networks is that they can't actually learn a distribution over a space of data straightforwardly. So basically you can't train them on an entire data set. You can only train them on a single image. So they can only represent a single image. So it's basically just in its current form, it's just basically a form of storage or a form of compression. It allows you to just store the data in this nice continuous form, approximated by a neural network. So you can't train it over an entire data set. So consider MNIST, for example, the MNIST dataset. And while it's true that you know the x, y coordinates of each image, you don't actually know the other coordinates of how the images interrelate to each other. So I'm just going to, if we click the SIREN page here, you can see lots of really nice examples in the video of how they fit to sort of, they fit to audio files. You can have a listen. And if we play it with a ReLU, it just sounds terrible. If you try it with positional encodings. And if we now use sine waves, it's really nice. And here's another example. Here's a video. I'm not sure if I can make it larger. And this is the SIREN network fitting to this video over time. This is the equivalent ReLU network. You can start to see the sort of piecewise linear artifacts, whereas the sine waves are fitting to all of the high frequency variations. And then they show fitting to various other equations, and it's nice to watch the video there. But it can only fit to a single piece of data. Oh, they also show it fitting to 3D meshes. And again, the SIREN approximation versus the ReLU version. And here's the SIREN. It's much higher quality. Okay, so that's SIRENs and that's implicit representation networks. And the problem with them is that they just fit to an individual image. They don't fit to an entire data set like MNIST. So to address this problem, Sam and I introduced what are called gradient origin networks, which are basically like autoencoders, but they're a little bit different, and they allow us to work with implicit representation networks. So with an autoencoder, you normally have an encoder and a decoder, and but what we say is we don't actually need the encoder. We can actually treat the derivative of the network as if it were an encoder. And if we look here, in this case, in the case of an implicit representation network, the problem is we don't know what this latent value should be here as we try to fit to a data. We know what the coordinates are for every image, for the pixels in the image, but we don't know this part here. We don't know what the other sort of coordinates of the latent encoding bit should be. We don't really want to use an encoder because that means we can't have the nice sort of representation abilities of, say, the sign nonlinearities. There are some other networks called hypernetworks which try to sort of estimate these values, or they try to sort of splice themselves in a bit like a sort of Borg sort of cyber thing which connects to everything in the intermediate network called a hypernetwork. But we really just show that this can be approximated just by using the derivative of the network, and it's very effective at doing that. So we start by basically initializing the latent space, or this unknown part at the origin. That's why it's called gradient origin network. And this is just a vector field of zeros at the beginning that we concatenate into the known coordinates. So we basically add this zero vector onto this. And then we feed through this sort of tuple, if you like, of the x, the y, and this big padded vector of zeros into our implicit representation network. And we get some prediction here, but the prediction, and we try to predict it for every image, so it's going to be just completely wrong at the beginning, like some blurry intermediate value or just some random value. But then what we do is we compute the gradient of the function with respect to these unknown coordinates, with respect to this z0 here, and we use this gradient as our coordinates. So we say z equals the negative gradient of the loss, like your mean squared error, between your input image and your prediction through this forward network with this 0 given at the beginning, and this gives us some actual coordinates for it. And then we basically take these new coordinates that we have and we feed it back through the network to get our final output, to get our final prediction. So the output is, we then get the outer loss, which is just again like the mean squared error between x, and feeding this new gradient with our coordinates back through. So it's basically like we take some coordinates, we take 0, we get this initial bad prediction, but then we compute the gradient of the function with respect to this value here to get some latent coordinates, like you have the encoder. And then you take this new distribution here, this part here, and you shove it back through the network with the original coordinates, and then you get an accurate prediction, and then you jointly optimize through all of that. So if you're interested in this, there's a project page you can click through, like the SIREN page. You can click through the code here, and you'll see the code is quite relatively straightforward to follow. In fact, I might just start with this simple non-implicit variant of the gradient origin network. This is just like a simple decoder, and but it's just like an autoencoder without the encoder. And we start by just taking some inputs, some x's, and we start with just a vector of zeros, and we feed this through our network, our decoder network, and we get some prediction. We'll call that G, and this is going to be really bad at the start, but then we compute the loss between the prediction and the original x, just the mean squared error, so this will be quite high. And then we compute the gradient of the gradient of the gradient of the function with respect to z, and we negate that and say that's our new latent points. And then we feed these new coordinates, these new latents back through the network, and now we get an accurate prediction. And then we compute the loss of this new accurate image back, and we compute that with x, and we backpropagate through the whole thing. So, and then there's the implicit variant here, which allows us to do it with implicit networks as well. Okay, so that kind of summarizes implicit representation networks, which allow you to well represent functions without using convolutions in a continuous way, and also how gradient origin networks can allow you to learn how to do that same approach over an entire space of functions, like a data set like MNIST. And we've also gone through some of the flow-based literature today. All right, so that concludes this lecture. I hope you have a good week.